Good morning, good afternoon, good evening, and welcome to AI for Good. My name is Bastiaan Kos of the ITU, the International Telecommunication Union, and it's my privilege to introduce today's webinar, Improving Rainfall and Water Cycle Projections Using Machine Learning, by Paul O'Gorman, Professor of Atmospheric Science at MIT, and Janni Yuval, also at MIT, as part of the AI and Climate series hosted by Professor Philip Steer, Head of Atmospheric Science at the University of Oxford, and Duncan Watson-Pearce, also at the University of Oxford. ITU is the United Nations Specialized Agency for Information and Communication Technologies, and also the organizer of AI for Good, together with 38 UN sister agencies, ACM, and co-convened with Switzerland. For today's discussion, we're counting on your active participation to create an engaging discussion, and we'll be using the Q&A functionality for that, which you can find at the bottom of your screen. So please post any questions to the panelists there. Additionally, there is a chat functionality, which you can use to communicate with other participants. Please make sure to send your message to all panelists and attendees, not just to all panelists. You can select that just above the message box. And with that, it's now time for me to hand it over to our moderator of today. Hi, Philip. How are you?
Hello, thank you. And thanks for joining, everyone. It's a real pleasure to introduce Paul O'Gorman and Janni Yuval. We will introduce both at a time and then hand over to them to do the session, and we'll take questions in the end, as Bastiaan just said. So Paul is really a leading expert on the hydrological cycle and atmospheric circulation, and with a real focus on the response to climate change and the long track record with many really great publications. And in a world of sort of increasingly focus on high performance computing, his work, which is generally leans on the underlying physics and some theory, provides often really nice, refreshing insights. So Paul did his undergraduate degree in theoretical physics and a master's in high performance computing in Trinity College Dublin. Did then a PhD in aeronautics at Caltech, and where he then also worked as a postdoc with one of our earlier speakers, Tapio Schneider. And then since 2008, he's on the faculty of MIT and rose through the ranks from assistant to full professor there. But in recent years, his research increasingly turned to apply machine learning to address some of the key problems in climate science. Again, always with a sort of a clear analytical view on the underlying problem. And Janni Yuval is also at MIT, and he also holds an undergraduate degree in theoretical physics and then worked in soft matter physics. Changed gears and to move to atmospheric dynamics for the PhD, has experience as a data scientist and in the software industry, and is now working as a postdoc with Paul. And today's session is on improving rainfall and water cycle projections using machine learning, and I'm really looking forward to the session. I hand over to you, Paul and Janni, and you can split it as you like.
Great, thanks, Philip. Let me just share my screen. Okay, thanks very much for that introduction. So yeah, I'm going to do the first half of the talk, and then Janni will take over. And this is collaborative work between us. And as Philip said, we're looking at how can we include machine learning in climate models, in particular to improve the water cycle. And I'll talk mostly about rainfall, but a lot of what I'll say could also be applied to evaporation and other aspects. And so this is part of an international project, M² Lines, with funding from Schmidt Futures, and we also thank the NSF and the MIT Environmental Solutions Initiative. So in terms of motivation, I think this past summer has provided plenty. There was many events, many extreme events around the world. I'm just highlighting two. One was severe rain and flooding in central eastern China. So that's what the image on the left is from. And then also in Western Europe, a more kind of a stationary weather system with very heavy rainfall over several countries. And these kind of events have major impacts on people, of course, on the landscape, as you can see here in this figure, and on ecosystems. So we really want to understand what's driving those events and how they are changing. In terms of rainfall, we can actually look at observations in a kind of a global view and see what's happening through the historical records. So this is showing changes in the wettest, how much rain falls on the wettest day of the year, normalized by the change in global mean surface temperature in degrees Celsius. And it's been aggregated into large latitude bands just to get a good signal compared to the noise, because there's a lot of noise in this kind of statistic. And what you can see is that it's positive over the northern hemisphere. We can actually see that rainfall extremes and precipitation extremes, including snowfall, for example, have increased in intensity in terms of this wettest day of the year. And there's very large erg bars here, particularly in the tropics. In the northern mid-latitudes, we've got a lot of data from rain gauges, and so there it's narrower. So we can see a signal from the observations. We know it's getting more intense, but the rate of change is not as well understood. And then the other big issue is that the pattern of change is not uniform. So if we look at climate models now, looking at future climate, this is the same kind of thing we were just looking at in observations, how the wettest day of the year is changing. Blue means it's getting wetter. And what you can see is it's blue over most of the world, but it's not a uniform change. For example, there's bigger changes over India, and then, for example, more modest changes over the Mediterranean. So what's going on here? Well, the overall increase is coming from what many of you will know is more water vapor in the air as it gets warmer. On the other hand, it's modulated by changes in the circulation, in particular how fast air is rising in these events in storms. And that's mostly what's giving us this distinctive pattern. And that pattern, that regional variation, really comes into focus if you look at northern summer, so June, July, August, now the wettest day in that season. And now you can see it's really quite heterogeneous. There are still large regions with blue increases in these heavy rainfall events. But then if you look over North America, parts of Europe, over Australia, you see little change or even declines. So, and again, this is due to the circulation changing, convection is changing, as we'll just talk about in a second. And we do see regions with very large pieces, for example, over India. So this is something we really want to understand well for impacts, such as we saw at the start in China and Germany and other parts of Europe. One problem is that these regional changes, exactly what we need to know, are quite uncertain. And that's particularly true in the tropics. So this is looking at heavy rainfall events. And blue, in this case, means that models are disagreeing with each other. And these are global models, and they really disagree in the tropics. And if I used a different color bar, you'd see they also disagree in other parts of the world. So that's a problem. And even if we put these models from around the world, here's 4 of them, in global models, if we put them in a very simple setting called an aquaplanet, where we just have an ocean-covered planet, so no land, no topography, so we're making our life easier in a way, the change they predict for a warming is very different for the different models. You can see the tropical rain bands are changing in all sorts of different ways here. And so this is a problem. Again, this is an idealized setting, but it's the same thing that's happening to some extent in our more realistic simulations. So why do we get these big disagreement between models? Well, for the intensity of rainfall, in particular the extremes or the weak rainfall, most of it is coming from the fact that we have to represent what's called moist convection or thunderstorms, cumulonimbus clouds, and so on in our models. But our models are shown here have grid boxes that are quite large, or could be 50 or 100 kilometers wide. And then these clouds are smaller or have components, aspects that are much smaller. So how do we deal with that? Well, we introduce what's called a parameterization. So this is a semi-empirical relation that tries to represent what's happening at the subgrid scale, so very small scale, say a kilometer scale, on the climate model at larger scale, say 100 kilometers. And so here's a classic version of one of these called the Arakawa and Schubert scheme. Really a great work, great ideas went into it. And it's based on a set of plumes that are rising in the atmosphere. And so they're meant to represent what you see in the real convection on the left. But this is a really hard problem, and people are doing it in different ways, different amounts of empiricism versus physics and so on. And so that's causing very big differences in the climate models in terms of rainfall, but also in terms of the humidity, the vertical temperature structure, other problems, and the circulation itself, because these are all coupled together. One point I just make is that this is usually done in a vertical column, as you can see here. So not, you just take one column of grid cells and try and represent the clouds and subgrid elements in that column. So we can see directly how that affects rainfall, here's the plot of how often it rains at different rates in millimeters per hour on the x-axis, and this is how often it's happening. And we have observations here in the black line. And so that's what we're aiming for. And then if we run our climate model with one representation of convection, we get this dotted line, and another representation of convection, these thunderstorms, et cetera, we get a very different line. And both of those representations from our climate models are not very close to what the observations tell us. And in particular, we see that there's problems not only for the high rain rates, which I've been talking about, but also the low rain rates. And you want to get both of these right if you're interacting with the land surface. For example, the flooding events we saw earlier cared about not only the rain on the given day, but also how much it was raining in the previous month. So that also matters. So what do we do about this? Well, I saw a nice earlier talk in this series by Bjorn Stevens, who talked about these global high resolution simulations, getting to say 1 to 4 kilometer horizontal grid spacing. And the idea there is you can explicitly represent the clouds, the deep clouds at least, and then avoid the need for this parameterization entirely. And so this is a nice example from one of Bjorn's papers showing observations on the left, and a global model will use a little bit called, or a model will use a little bit called SAM. And these were the model was initialized with the observations not, long before. And so even the patterns agree, and you can see you get a lot of fidelity with that approach. So there is one hitch here, which is that these very high resolution models are too expensive to run for the long timescales we have in the climate system. So for most things we'd like to apply climate modeling to, that's a problem. So this is showing, this graph is a nice graph showing how long it takes the temperature at the surface of the Earth to respond to an increase in CO2. So it's an idealized experiment in a model, global coupled climate model, where you suddenly increase the CO2 or decrease it, and say, how long does it take for the fraction of the total response to reach 1? And what you can see some interesting things, the Northern Hemisphere and the Southern Hemisphere are different, for example, but the main point is look at the x-axis here, thousands of years, right? So 1,000 years, something like that. That's just for the surface temperature, not the deep ocean. So we need to run these models for a long time. And if we have to resolve convection, that's going to be a problem. So one other approach is used, which very commonly, which is to say, well, I don't want to worry about the whole of the Earth. I will just focus in on one region, say, for example, North America, and then I can use my high resolution model there. And this is very common. Of course, it makes sense, particularly if you're interested in impacts, but it does also have some limitations, which is that you still have boundaries, which can be a problem. And you have to provide information at the boundaries, and that comes from some global model, which has all the same problems I discussed earlier. And then another problem that may not be as obvious, but it matters for the scientific part, which is that if we have these kind of small regional windows into what's happening in several different parts of the world, it makes it very hard to get a global scale understanding of what's happening. If you recall, when I was showing the patterns of extreme rainfall change earlier, there was these very distinct very large scale patterns. And so if we want to understand what's going on, I think it would be great if we could have a global view. So to summarize the current situation is we have our climate model on the right with its grid boxes. To the extent we can, we're resolving the flow and what's happening in those grid boxes at large scales. But then when we want to look at what's inside the grid box, I should have said we use these subgrid parameterizations, for example, based on a series of plumes. And so what we want to look at now for the rest of this talk is a possible way forward where we still keep our climate model, keep the laws of physics for all the resolved motions, but instead of having our semi-empirical relation, we use machine learning to train a new parameterization that represents how the small scale effects are affecting the large scale, but trained now on a very high resolution model that we can run not for the climate studies we'd like to do, but long enough that it can it can be used to give enough training data to learn this parameterization. So that could be a year rather than 300 or 1,000 years, something like that. And so in that way, we can take advantage of the high resolution models, but still be able to do our climate studies. So what are the opportunities from this kind of approach? Well, I've cited some papers below. This is a very exciting area with a lot of work from different groups around the world. One is, I think it's already been shown that machine learning, by incorporating machine learning in the climate models, we can outperform the conventional approach for things like rainfall statistics. We also can have a more flexible structure. I mentioned earlier, we usually are just considering one column, one atmospheric vertical column, or one column in the ocean for these parameterizations to represent things like convection. And that's partly based on our understanding of physics, which mostly goes in the vertical there. But if we use the machine learning route, we're not as tied to that, and we can now maybe use more inputs non-locally. Janni will talk about that later. And then more generally, we could figure out, well, why are those inputs helping? And could we learn new physics that could go back into a more conventional approach that might have some other advantages? So I think there's multiple ways in which this kind of approach can be helpful to us. There are, however, challenges. This isn't operational in climate models yet. One problem is that when we incorporate machine learning in our climate model, we're now mixing a physics-based model and chemistry-based model with this machine learning component, which could be a neural net. And how that will actually behave when it's all coupled together is not very well understood. And sometimes it leads to instabilities where temperatures will suddenly increase very dramatically, or winds, or when it might work for weather forecasting of, say, 10 days, but then if we try to run it for many, many years, there can be a drift problem. Another, what I might call a quasi problem, is that if we train our machine learning algorithm in one climate, it will often not work in another climate. So we can get around this by training on a warmer climate also. So we run our high resolution model for a year in a warmer climate. But it would be great if we could somehow learn something that would extrapolate to different climates, because then, for example, perhaps we could learn from observations as well. And then another problem is that the machine learning parameterization, if we do this blindly, will not know, it won't know about things we do know about the physical system, for example, that it conserves energy or water. And so ideally, we would like to build those in. So the remainder of the talk then will first involve talking about an approach to doing this, including machine learning in climate models that works well for precipitation in its extremes, while being stable and robust. And then Janni will take over and discuss some questions at the frontiers of how we include machine learning in climate models. So here's a movie of the high resolution simulation we're going to learn from. I heard earlier it may be a little jerky, so I'm looking at a beautiful, beautiful high resolution movie. You may not be seeing that, but hopefully you can see this is the outgoing radiation, and you can see things that are clouds essentially. You can see there's two rain bands in this particular setting, and then there's mid-latitude cyclones and anticyclones. So we have in one simulation a lot of the properties that we'd like to learn about. We're using SAM model of Murat-Krudinov. We use a trick, which I won't get into, which allows us to use a grid spacing that's a bit coarser, about 12 kilometers, which is effectively about 3 kilometers. So it's in the range of what we would think of as these convection resolving simulations. And then to keep things simple, we prescribe the sea surface temperature. So we're not simulating the ocean, and we set it to be symmetric about the equator. And so this center part is the tropics. It gets colder as you go poleward in both directions. So this is, I think, a great test case for us to try and learn from. But you might say, you might be somewhat skeptical. It is very idealized. How does it relate to the real world? Well, we can compare the rainfall distribution, how often certain rain rates occur in millimeters of rain per day. The high resolution simulation we're using is shown here in green, and the observations are in red. And the observations are just choosing a part of the Pacific Ocean that's pretty similar to our tropics in this high resolution simulation. And you can see they agree not perfectly, so it is in an idealized domain, for example, but they agree pretty well. If you compare it to a well-known global climate model, CESM, you can see that it's doing quite a bit better. This particular model global climate model underestimate extremes. Sometimes people say that climate models always underestimate heavy rainfall. Actually, sometimes they overestimate it. It depends, but this particular one does underestimate it. And you can see it's drizzling and so on too often, too much moderate rainfall. So our high resolution simulation is a good target for us because we want to do well on rainfall in particular. So then we can take the same model and run it at our high resolution and then a coarser resolution, 8 times coarser, and without adding any machine learning yet. And you can see that changes things drastically. Instead of having 2 rain bands, this is the mean time average amount of rain versus latitude. So in the higher resolution, more accurate simulation, in this particular configuration, you get 1 rain band and the south of the equator, 1 rain band north of the equator. If you make the model coarser, 8 times coarser grid spacing, suddenly you have this very, very strong rain band right at the equator. And similarly for extreme rainfall here, the 1 in 1,000 event of 3-hourly precipitation, so these are rare events, you have much too heavy rain rates at the equator. And this is very common in models that don't resolve convection well. That's what you tend to get. You get these kind of explosive storms that have very, very heavy rain rates. Okay, so how can we introduce machine learning? Well, what we do is we take our high resolution simulation and we do what's called coarse graining. So it's kind of averaging, coarsening up the field. So here's, I think it's water vapor in the atmosphere plotted versus latitude and longitude. We're blowing up this little region in the tropics. It has some detail, and then we coarsen it by averaging over 8x8 grid cells. And what we'd like to do then is learn the impact of the processes that are happening in the very high resolution simulation that are not captured when we go to this coarser resolution. And we're doing it, as I said, in this one column by column, basically. So what are the kind of processes we worry about? We have vertical movements by the vertical wind. We have turbulence that occurs primarily near the surface. We have evaporation, importantly, at the surface, which we try to correct for the change in resolution. We have radiation in the atmosphere and at the surface. And we also have what's happening in clouds, which is called microphysics, so rain formation, things like that. So these are all things that are happening at too small a scale to properly resolve, and we want to learn something about them. Okay, so what do we do? Well, this is the approach we use. We calculate what we want, the effect of the subgrid, the small scale on the large scale. We do this exactly by going to the equations of the model and coarse graining those equations. And we do it process by process. And so this is a very laborious task, which Janni in particular has done a lot of work on. The payoff of doing it that way, that very careful way, is that you get very accurate results and you get a lot of flexibility because you can treat each physical process separately and respect its particular properties. The other thing we do is we want to conserve water and energy appropriately. So that it depends what algorithm we use. So if we use a neural net, we use a deep neural net. What we do is instead of just predicting the net effect at a given level in the atmosphere, given altitude in the atmosphere, we predict the fluxes and the sources and things separately. And that allows us basically to conserve water and energy. I'll show you how that works in a second. Or we can do an alternative algorithm called random forest, where the predictions are averages over the training samples. If the training samples themselves conserve energy and water, then the predictions will too. And so that is an advantage of using the random forest. So going back to the neural net, this is what it might look like. You have some inputs, which are moisture, temperature, and wind in the atmosphere. We then predict sources of moisture. This could be how much cloud is converting to precipitation. We have upward and downward fluxes of water. We have turbulence, which we estimate a diffusivity for. And then we make sure we're consistent because we're doing it process by process. If there's a moisture source, and we make sure that's consistent with the energy source that we're prescribing. So this is just giving you a flavor of the kind of approach we're using to try and make it consistent with the physics we know. So here's an example of this working. It does work. So here's the amount of water in the atmosphere. You see these 2 rain bands here in the tropics. Here's when you run it at coarse resolution. Okay, we haven't added any machine learning, so we know it's not going to look very bad. It's got this one very, very strong, unrealistically strong rain band at the center. And now we incorporate into the model, the SAM model, or neural net. We just include it as one component in the model. And it runs pretty quickly. That's not a big problem. And so if I just press play here, we start with the same initial condition that comes from the coarse resolution simulations that has that one strong rain band. And then gradually you can see it evolving towards the high resolution simulation. So we can see those two rain bands appearing. For those of you who know about climate modeling, sometimes two rain bands are thought of as a bad thing because sometimes you get that too much. But for this particular setting, that's what the high resolution simulation gives us. And this simulation can be run for as long as you want. We can run it for years. It's stable, and we can then collect statistics and say, well, how's it doing for the climate, the climatology? And so here's the time average rainfall versus latitude. The high resolution is in blue. We see those two rain bands. Coarse resolution without any machine learning is in green, very, very different. And now in this case, we've added in a random forest, and you can see it really improves the mean rainfall distribution. And similarly, this is what really got me excited about when I saw these results first, is if we look at the extreme rainfall, this is the thing that I was talking about a lot at the start that's very difficult to get right in climate models, and they're all disagreeing on in the tropics. Well, here we see that adding the random forest in this case has really improved the extreme rainfall distribution. So this, to me, is really amazing result, and it's not very expensive when you've added in the model. Okay, so now I'm going to hand off to Janni to discuss some questions at the frontiers of including machine learning and climate models.
Okay, thank you, Paul, for the introduction. I hope you can see my screen. Please shout if you don't, if you can't. So as Paul said, I'll discuss some questions at the frontiers of including machine learning and climate models, and I'll go over them kind of one by one. So the first challenge we want to address by using machine learning is the question, can we use machine learning convection parameterization to perform well also in what is called the gray zone? So first, let me introduce what is the gray zone. So in this plot, I'm showing in the y-axis the skill of different models to simulate correctly the daily cycle of summer precipitation in Germany. The x-axis shows the resolution of different model runs. And you can see they're kind of split into two. So the bottom line shows you simulations where when deep convection parameterization, traditional deep convection parameterization is used. And you can see the performance is pretty poor. So basically, when we use deep convection parameterization, we cannot simulate well the daily cycle of summer precipitation. However, when we turn off this deep convection parameterization, all of a sudden, the simulation improves dramatically. And the reason that this is the case is because when we get to certain length scales, typically grid spacing below 25 kilometers and above 1 kilometer, we partially resolve deep convection. So these kind of deep convection parameterization schemes, which are not scale aware, have kind of learned something which is not correct anymore because convection is partially resolved at these resolutions. So basically, the bottom line of this slide is that traditional convection parameterization does not work well in this grid spacing. And this grid spacing, let's say 25 kilometers is below. In the next few years, it will be more and more accessible in climate models. And climate models somehow will have to deal with the fact that they cannot use traditional deep convection parameterization in this scale. So the question is, how can we use machine learning to tackle this specific issue in climate models? Can machine learning work well in the gray zone? So how can we test this? So the idea is the following. Here I'm showing again a snapshot of our high resolution snapshot from the model. It shows the amount of water in the atmosphere, basically water vapor. And I'm just zooming in into an inset. And on the right, each panel shows how different coarse graining or different horizontal averages would take this high resolution image, which has this kind of small scale features, and how it would look like when we coarse grain it with different factors. So X4 means we just took 4 by 4 pixels, 32 means we took 32 by 32 pixels. And you can see that as we coarse grain by a larger factor, we lose more and more of the details that the high resolution model contains. And the problem with this gray zone is that it's a region where we partially resolve convection. So the idea in machine learning parameterization, since we directly rely on high resolution simulation that we think that they represent deep convection pretty good, we can now train different models, different machine learning models for different scales. Namely, for each of these coarse graining, we will recalculate the effect of convection on our result scales and try to predict it. So let's see how it looks when we really take models. In this case, I'm showing you the scale of different, this hybrid model, climate, this atmospheric simulation combined with machine learning parameterization that run at different coarse graining factors. So meaning, so 32 means it's a relatively large grid spacing, X for relatively grid spacing that is closer to the high resolution case, and the y-axis shows the scale of how well we simulate precipitation. And you can see that as we increase the resolution, we perform better and better in terms of simulating correctly the precipitation. Just a side comment, what do I mean by simulating correctly the precipitation? On the right, I'm showing such a typical case when we compare the high resolution, which is our target. This is kind of the best scenario we can get, compared to how a random forest parameterization would do. Like running this kind of atmospheric simulation with a machine learning parameterization, you can see that they are fairly close. So as we increase resolution, we improve. And this might sound okay, trivial, but remembering that in the gray zone, we usually fail using conventional parameterization, this I think is evidence that machine learning parameterization can really kind of close the gap. And in climate models that will run below this kind of, in this gray zone, let's say below 25 kilometers, maybe machine learning parameterization are the key to kind of take into account the effect of deep convections, which are just partially resolved. The next question is whether machine learning can really generalize well to warm climate. And Paul has mentioned it. This is kind of crucial because eventually we want to use this machine learning parameterization for the question of, let's say, how the response of precipitation to climate change. And in this plot, I'm showing it's taken from this paper by Paul and John Dwyer, where they try just to test if a random forest parameterization can emulate the result of a typical or a traditional parameterization. So what is shown here is the response of precipitation in the y-axis to warming as a function of latitude. And the black line shows what happens when we use kind of traditional scheme. The red dotted red line shows what happens when we use a machine learning scheme. And the point is that they are the same because we just emulated them. But the catch here is that we let the random forest to train both on the control climate and the warm climate. However, in the real case, you might expect, okay, maybe we don't know what the warm climate will be. Maybe we want, and maybe more broadly, we want a parameterization to kind of be able to simulate a range of climates correctly. So we can ask the question, what happens if we repeat the same exercise exactly and just let the machine learning learn just from the control climate? So this is what is shown here. And all of a sudden, you can see that there is a huge gap between the black line, which is what we try to emulate in this case, compared to the red line, which is now relies on machine learning, but has never seen the warm climate. So when we really try to simulate, it performs really, really poorly. So this is a problem, and I just mentioned that the paper by Stefan Rasp has already shown that machine learning algorithms can reasonably interpolate between climates, but when we get to extrapolation, they perform really, really badly. And to put just be more focused, what do I mean by extrapolation? To this, I'm plotting to show what do I mean why climate model, why the machine learning needs to extrapolate. I'm showing here the probability distribution of moisture, which is one of the inputs we typically use in machine learning parameterization and any parameterization for two different climates, for a control climate and a warmer climate. And the problem starts when we have values that are never observed in the control climate. If we only train on the control climate and try to use parameterization in the warm climate, we will fail because there are values that are never observed in our control climate. When, let's say, climate warms, we have more moisture in the air and we get to values that we have never seen before. So to tackle this problem, Tom Buechler, and we are involved as well, has suggested the following idea. So at the moment, I'll introduce two kind of ideas. One is brute force, which is what we have been doing so far. We will take each line here represent, let's say, different climate distribution, PDF distributions of a certain variable. On the left is the inputs, on the right is the outputs. So you can see that we take, let's say, inputs, which has no overlap, And a brute force approach would just try to use these inputs, learn from these inputs only from the control climate, and to predict outputs, which again, they don't have an overlap. When we try to predict the outputs, the effect of convection on the result scales, they won't overlap with each other. And this brute force is kind of doomed to fail because it basically enforces us to extrapolate. But the idea is maybe we could find climate invariant variables. So use some kind of mapping to rescale input somehow, such that we will find inputs that does not change substantially their distribution when climate warms or climate change in general. And find this kind of invariant mapping where different climates, their inputs and outputs completely overlap. And then eventually go back and ask, okay, what's the real output we need with like inversing this mapping? And let's see how it works in practice. So we have, let's say, I'll first show what happens when we, again, train only on a warm climate, but predict for the, train only on the control climate, predict for the warm climate. I'm showing here the scale in terms of R squared, pressure versus latitude for such a neural network. And you can see, and one means it predicts very accurately, but in most regions, this tropical region, it completely fails. In this case, this is the brute force approach when we use temperature and specific humidity as inputs. And the reason that it fails, because in the tropics now, it's warmer than before. The machine learning has never trained on such a warm climate and it just fails. But the idea is that we can rescale now the variables. In this case, we rescale to buoyancy instead of temperature and relative humidity to specific humidity. And when using such scaling, now the two distribution completely overlap. So both control climate and warm climate have a full overlap in their distribution, and we try to use this in practice. And now when we train only on the control climate, but try to predict on the warm climate, we kind of succeed. Look on how accurate it is in the tropics, especially if you compare the reference that we had before. So basically what we show is that by using such climate invariant inputs and outputs, we can better generalize to unseen data. And also we find it also that we can generalize better when we train on an aqua planet and try to test it on a real geography. I should say, when I say we, it's mostly Tom did this work. And interestingly, when you ask yourself, okay, why climate invariant inputs work better, except for the fact that there is a full overlap, when we test like on what the prediction relies on, we find that it relies this kind of prediction on a more local in the vertical, local features to predict the local outputs compared to a very non-local in the vertical case when we use the brute force approach. And so the last point I want to talk about is kind of going beyond the traditional approach. So Paul has already mentioned that a traditional approach is taking a single column in the atmosphere, using inputs, temperature, moisture, and so on, and try to understand how the subgrid processes, such convection, clouds, and so on, would affect these variables that we do resolve. However, if you really think about like processes in the atmosphere, let's look on mesoscale convective system. A mesoscale convective system has like a typical area of 100 square kilometers, and it is driven by small scale convective processes. But if we take this mesoscale convective system and just like put it on our climate model on the grid, you would see that it is larger than any single grid point. So you can wonder, maybe in order to try to approximate the effect of subgrid processes in a specific atmospheric column on the variables we do resolve, we need more information than just from a single column. Maybe we need to take information from the nearby atmospheric column, which I'm going to refer here as a non-local parameterization in the horizontal. And not only the motivation from some kind of mesoscale convective system, we can also look at processes in the atmosphere that we know, such as lengthwise convection. What is lengthwise convection? It's convection occurring on a lengthwise path. And you can imagine if this lengthwise convection is not resolved in climate models, but it does involve maybe exchange in the horizontal, like convection that crosses the boundary across this kind of neighboring grid cells, we would need more information in order to kind of predict it accurately. So what we do, we just, since we have a neural network, we can just train a neural network with this kind of non-local approach. And this is the one advantage of neural networks. We don't need to formulate a full theory before even testing the idea. So what am I showing here? I'm showing the performance of the two different networks. One is the single column network in blue. So far that we used, and kind of all traditional approaches and machine learning approaches use a single column parameterization compared to a non-local, the 3x3 parameterization. And you can see that the non-local parameterization performs much, much better. So I think that this is pretty exciting that we have these results, that we have kind of a new information that we can provide a network. It substantially improves its performance. But I think that for many scientific purposes, this is really not enough to have this tool that just, let's say, predicts better than its predecessor. We really want to understand why it predicts better, and maybe even zoom out. We want to understand the physical system better, which processes were not modeled correctly, let's say, when we try to use only a single column parameterization. And luckily, in the recent years, we have more and more tools which are usually referred as interpretable machine learning tools, which help us kind of to open these kind of black boxes of neural network and peek into them and try to understand how they make their decisions, on what do they rely. And I think that these kind of explainable artificial intelligence tools can be a real game changer if we are talking about scientific applications, because we can now use them to understand better our system rather than only provide better predictions. So let's see how it works. I'll introduce one such explainable artificial intelligence tool called layer-wise relevance propagation. And then I'll try to take the same tool and implement it and use it for our purposes, for the question of convection and non-local convection, non-local parameterization, and why it performs better. So here I'm showing a vanilla task for a machine learning. For some neural network, the input will be an image, the output would be the probability we see a cat in the image. This is a vanilla task, but the explainable tools, what they allow us to do, specifically, again, here I'm using layer-wise relevance propagation, is we can take this prediction of the network, we can now ask which region was most informative for the prediction. So in this case, you can see that the heat map showed that the region of the cat was most informative. And this gives us kind of a sense of confidence that we are not relying, let's say, on the background where there is nothing special for a cat in the background. So let's see now how can we take this approach, take our problem of non-local parameterization and try to understand better why our non-local parameterization performs better. So as a first step, let's take just snapshot of cases we do substantially improve our prediction compared to snapshots that we don't improve the prediction. So first, let's look at the top 10 images. And what you can see is that these are cases where when you use non-local parameterization, we all of a sudden have substantial improvement in the ability to represent the subgrid processes we want to predict. And you can see already that there are common features in these 10 plots. You can see that basically we see fronts. There are kind of sharp features. I should say colors are indicating the cloud cloud mass per unit area. So you can see where the clouds are, and you can see that basically they are fronts. When we look at similar cases, but where we not improve, the non-local parameterization does not help us to improve the prediction, we get very different shapes of clouds. They are more diffuse, they're dispersed, they are not so sharp features. And now we can take these improved cases and ask the same question we ask for the cat. Where the network look to determine the effects of convection. So we do that. And on the right, I'm plotting here 3x3 boxes, which represent this kind of 3x3 boxes of the non-local parameterization. So we try to predict the effect in the center column, but we use information from the vicinity. And I'm showing here 4 different features that we use as inputs to the parameterization, which are the temperature and moisture. These are common to any parameterization, and zonal wind and meridional wind. So let's see what we have here. Color, like larger number or wider color, shows regions where the network really use this information. So what we see, we really use information from center column from the moisture. This is not surprising. Every parameterization relies on that. Similar can be said on the temperature. But what is surprising, or at least interesting, is that now when we look at non-locally, we really rely when we look on the zonal wind and meridional wind, we rely on grid points, which are not the center grid points where we make our prediction. We rely on grid points which are non-local. In the case of zonal wind, to the west and east of the center grid point. In the case of meridional wind, north and south of the center grid point. And I think what is interesting is that parameterization really learned from non-local wind. And in this to be submitted preprint, we show that it basically relies both on the divergence of wind and also the non-divergent wind. And I think this is very interesting, both because it introduces an avenue that we can improve machine learning parameterization, but even can provide ideas to how to formulate new parameterization, traditional parameterization, and on what they should be relying when we develop such parameterizations. As a kind of final slide before the conclusions, I want to kind of show the kind of what is happening and what has been happening in the last few years in the case of how we are building this model. So the final goal is that we will have some kind of an operational hybrid climate model that will allow us to simulate better precipitation and give us more confidence on what will happen in the future, get better projections and so on. But I think we are not yet there. And I'll introduce kind of what was happening, I think, in the last, I don't know, 5 years or 3 years in this hybrid model community. So I think most of the problems that we discussed today and many other works are still providing proof of concepts. So this is both that machine learning can run stably without climate drift. It can emulate traditional parameterization. It can learn new parameterization that are even more accurate from high resolution models and kind of test it on idealized cases. But as the years will pass, and already this is occurring, I think more and more we will kind of trying to push it to the more and more realistic cases. So starting maybe with an aquaplanet, just a model that does not have orography and land, and test how can we use machine learning in this context, and try to learn what things work, what things fail, what causes instabilities, how can we further improve the accuracy of such models, and eventually, of course, trying to test it in a more realistic climate models that include land, orography, and other components before we really can go to having an operational hybrid climate model. So just to conclude, I want to say that I think we show the potential here that using machine learning to improve the predictions of rainfall and water cycle. And I think this is really necessary because water cycle is changing in current climate, in our climate, but models do not currently correctly simulate rainfall for either extreme cases or for low intensity events. And there are many opportunities to use machine learning in such a hybrid setting and in climate models. And the potential is to improve the accuracy and build better parameterizations. And of course, we need to verify that we can run them stably and so on. As Paul discussed, we show that we have the potential to use such machine learning parameterization in the gray zone, where basically traditional parameterization fail, and soon global climate models will run at these resolutions at, let's say, 25 and kilometer grid spacing or higher grid spacing. We will have to somehow deal with the fact that we have this gray zone. And finally, we've shown that kind of we are not obliged to use kind of the traditional approach of single column parameterization. It's very easy to kind of test new ideas like this non-local parameterization, maybe including memory in the future and other stuff. So with that, I want to thank you and happy to get any questions.
Wonderful. Thank you very much, both Janni and Paul. It was really interesting to see the work up to date and some of this latest work as well. It's looking really good. I'll kick off the questions. There was a question in the Q&A. I think this popped up during your talk, Paul. It's a bit of a more general kind of climate question, but we have a broad audience, so it'd be great if you. They were wondering why, often when you see these projections, you see climate models go out as far as 2100, and the issue was asking if that's something to do with the accuracy of the projections, or do uncertainties dramatically increase past that point?
Yeah, that's a really good question. Yeah, so you have sources of uncertainty from the modeler and what we're emitting into the atmosphere, and there's many factors that contribute to uncertainty. But I think we do run models for longer than that, but those are just the results you tend to see, some kind of target like 2100, like I showed earlier. But we do indeed run them for much longer for future scenarios. It's just the uncertainty gets larger as you go out, and also for past climates it's also used. So yeah, there isn't a magic number about 2100. Often people actually nowadays are interested in shorter time horizons and getting some good information for that.
Brilliant, thank you. Janni, this one's probably more for you. So do you foresee any special challenges when switching from the aquaplanet configuration to a more realistic model?
Yeah, so I think there are multiple challenges, and we are kind of experiencing these challenges today. And I think a lot of them is related to the fact that different climate models, they are formed differently, they use different prognostic variables sometimes. And even more kind of rooted than that, some parameterizations in current climate models are talking with each other. So let's say, I don't think that we would like to completely change our radiation scheme, which are pretty accurate generally. I don't think we want to change it with the machine learning parameterization for several reasons. A, because we know we have pretty accurate parameterizations for radiation, but more than that, if you really want to train a machine learning parameterization for radiation, you would need to include all the information regarding all, let's say, the tracers, the relevant guesses. You would need to basically build a huge data set, which I don't think it's feasible, and I don't think we need to do that. But that raises another question, because let's say a radiation parameterization is relying on certain other parameterization to get certain inputs that related to certain penetration depth and things like that. So basically, current parameterizations, how climate models are built, are not completely decoupled from each other. And we would probably want to change some of the parameterizations, but it's not an easy task because we need to understand how to basically make everything still consistent. So let's say if we want to keep the parameterization for radiation, we would need to somehow provide some information that is currently provided by a different set of parameterization, which are traditional, which we will want to change.
I think.
Great. I might come in with a question here, and that's more a general question, and in a way an obvious question, but you rely for much of the work on SAM as the truth, and we know from many cloud resolving modeling studies that cloud resolving modeling differ in their answers to certain questions. So in a way, the obvious question arising is what is your vision, or what are your strategies for incorporating observations in as well as additional constraint? You probably have thought about this already.
Yeah, as part of the project we're involved in Squared Lines, there's one half, which is basically what we've been talking about for both the atmosphere and ocean, but also then bringing in observations using, technical term data simulation, but basically what's used now for bringing observations into, for example, weather forecasting. And so, yeah, I think that's the route to go, is to try and combine them both and to, include as much of the physics in this indirect route via the high resolution simulation that you train on. But then if you want to correct biases in the model and get it closer to the real world, I guess, importantly, for practical purposes, perhaps you have to include a step where you learn from observations as well. But I think that's still a very open question, how best to do that. I don't think people have figured out what is the right way to do that yet. So it's a good question indeed.
There's a related question actually in the chat. So when you're looking to build models for, well, okay, how do you consider rare events such as La Niñas and El Niños? I guess in both the training data and the algorithm, how do you account for that in these developments?
Yeah, I mean, I think that's a really good question, actually. And I think that relates to what Janni was talking about, this idea of generalizing to very different climates. He was talking about generalizing to, I don't know if you noticed, but it might have been written on there, but it was like +4 degrees Celsius, +8 degrees Celsius, really big changes. But I think that's an interesting and very hard test to look at. But if you can get approaches like Janni talked about and that Tom Buechler is doing that work for these big changes, I think that will work well for something like El Nino, where you do get warmer, but not by the same amount. So I think that kind of approach is good. It's kind of ensuring that you've got a good physical basis for your parameterization. But yeah, I think also you would just want to train on El Nino years, for example, if include those in your training data where possible. So that is a complication, but perhaps this smart choosing of input and output variables might help with that.
Yeah, I really like that approach. Actually, it looked really nice. I wonder, actually, maybe Janni, to you, are there ways we can learn such invariances directly from the data? Because as cloud physicists or modelers, we have the intuition that maybe we remap it onto this space and it has such an invariance, but that's not always obvious, right? And other parameterizations, it might not be so simple. So have you thought about that at all?
So, I mean, I should say that this climate invariant mapping is done using some like knowledge from the basic physics or climate physics. I mean, maybe some machine learning could learn to find such parameters or such variables, but let's say using relative humidity, I think many, let's say, modelers would say, yeah, it's a quantity that doesn't change much. Whether it's going to work or not, it's a question, because maybe it's not sufficient information. Even if you find such an invariant mapping, it doesn't guarantee you'll have a good mapping, even if you use such kind of data-driven schemes, because maybe it's just not enough information really to predict the outputs that you're trying to predict. I think realistically, if we're talking about like operational case, we would have to train on various climates. I mean, and I think that different papers have shown why, let's say, you can generalize, let's say, across latitudes. Let's say you get warmer, if I can try to get back to that, but we still had very good performance in the extratropics, and you can wonder, but why? Like the climate has changed, and the reason, like I'm referring to here, you still have very good performance here, and the reason is that you still have the same kind of distribution of inputs and outputs, probably because maybe you went 8 degrees warmer, but you still have in certain regions the same distribution. So if you would be able to learn across, let's say, your training data will be built from various climates, I think it would add a lot to the fact that you would be able to generalize. I mean, this was kind of a nice romantic approach, which I think we should use, but in practice, we will also use, I think, like many different climates during the training setup.
Great. Maybe just a quick question. The non-local approach was very, very interesting, and the results obviously were quite convincing and physically plausible. So that's nice. You picked this 3 by 3, but it's not obvious that that's the right length scale necessarily of influence. Is it just initially as a scoping exercise to see what the non-locality does, or have you tried sort of wider domains of influence?
Okay, so I'll answer that. So the reason that we chose 3 to 3 is that it would be possible to really implement in models. I mean, if you would say to me that this relevance scale, you need to 20 by 20 grid points, the problem is that it would be very difficult to implement in real models where they solve a certain domain and they don't have the information that you would need to inject into the parameterization, because they don't include the information from, length scale of, I don't know, 1,000 kilometers away. So this is from the practical point of view. I think at some point, if you would discover that what you need is really long, like large length scale, it won't be useful. So this is from the practical point of view. And I should say that I've seen a talk in part of the project that we're involved in M2 lines, that they show that actually non-local in the ocean, the case is different, that they really need to go farther away to really improve parameterization. And when you look close enough, you don't get any improvements, but you go far enough, you start getting substantial improvements. And it's a question why, and I think it's undetermined, but at least for the atmosphere, I mean, we haven't tried a very large domain for the reason I mentioned. We don't know for effect if this is the exact range. And also remember that it really depends on in the first hand on the scale of the grid point. So what is the relevant scale? It's not only like the number of grid cells, but also related to what is the resolution that your base model is run at.
Great.
Just quickly add, I mean, I think the issue there is that the big issue is that when people run climate models, they split different parts of the globe onto different processors or cores, in particular the processors. And then you could, in principle, get the information from very far away across the globe, but you have to communicate to a different processor. And so that's that's a disadvantage. So maybe there's a trade-off there.
Yeah, no, that's great. Well, this was a really fascinating session. We could talk on and on for a long time, but we shouldn't because we're out of time. So thanks a lot to Paul and Janni again for really fascinating talks. This was really great. And for everyone else listening in, I encourage you to stay tuned. So we continue actually next week with collaborators that Paul already mentioned. So it's on bridging observations and numerical modeling of the ocean using machine learning. And speakers will be Laure Zanna and Julien Braillard. So tune in again next week, and you can also obviously follow the talks back in YouTube and rewind them as much as you like. Okay, thanks again to both of the speakers, and back to Bastian.
Thank you, Philip and Duncan, for moderating, and a big thanks also to our speakers, Paul O'Gorman and Janni Yuval. As Philip already mentioned, we have an upcoming session next Wednesday, the next session in the AI and Climate series. Tomorrow, we also have a session with our partner on AWS on startups in emerging industries. That information you can also find in the chat. For other information, future sessions, please have a look also at aiforgood.itu.int. And with that, I would like to once again thank our hosts, Philip and Duncan, our speakers, Paul and Janni, you, our participants, our sponsors and co-convener Switzerland, and we hope to see you soon. And here's a quick poll. Please let us know how much you liked the session.
Selector, rewind selector, rewind selector, rewind selector, rewind selector, rewind selector. Selector, rewind selector, rewind selector.